Hi learners. In the chapter application of derivatives, we already studied about increasing and decreasing functions, tangents and normals, and today we shall learn about maxima and minima of a function. That is, at which point a function attains maximum value and at which point the function attains its minimum value. And we shall learn very interesting examples also. Consider the graph of a function, and you can see when x equal to 4, the graph is having a maximum value. That is, it is having a peak point. And at that point on the curve, you can see there is a horizontal tangent like this. And for the points on the curve where x value is slightly less than 4, what will happen to the tangent? Let us see, the tangent will have a positive slope like this, means derivative positive at all those points. And at the point where the maximum attains, the derivative is 0, means a horizontal tangent like this. And for the points on the curve where x value is slightly greater than 4, what will happen to the tangent? Let us see, it is having negative slope like this. That is, at the point where the maximum occurs, tangent is horizontal, means the derivative is 0, and left hand side positive slope. You can see at the right hand side it is having negative slope. This way we can identify the point of maximum. And consider the curve. This time it is having a minimum value when x equal to 7. And at that point on the curve we shall have a horizontal tangent like this. And for the points on the curve where x value is slightly less than 7, you can see the tangent is having negative slope like this. And where the minimum value occurs, you can see at that point on the curve we shall horizontal tangent, means the derivative 0, and for the points on the curve where x value is slightly greater than 7, we shall have a positive slope. This way we can identify, that is, from negative slope to 0 to positive slope means where the tangent becomes a horizontal, where the derivative vanishes, that point will be a point of minimum for the function.
Look at the graph. If we consider the interval, say 1, 3, you can see that at x equal to 2, the curve is having a peak point. Capital A on the graph refers to that. So we can say that x equal to 2 is a point of local maximum, and the value of the function at x equal to 2, that is this height, here it is 6, the value of this function is what is called the local maximum value. Similarly, for the interval 3, 5, you can see that the function is having a minimum value when x equal to 4.25. That is, at x equal to 4.25, the function is having a minimum value. So we can say that x equal to 4.25 is a point of a local minimum, and the value of the function at that point x equal to 4.25 is called a local minimum value. Similarly, again, when x equal to 5.86, the function is having a local maximum, and capital C refers to that point. So x equal to 5.86 is called a point of local maximum, and the value of the function at that point x equal to 5.86 is called a local maximum value of the function. Consider a problem. Find the point of local minimum for the function small f given by f of x is equal to x squared minus 5x plus 6. And as the graph shows, the graph is a parabola and it has a minimum value at x equal to 2.5. Graphically it is very clear how to find that point, that is x equal to 2.5, which is here a point of local minimum, how to find that point, how to locate that point using calculus. So here we can use the calculus in a very fantastic way to find that point x equal to 2.5, which is a point of local minimum. Here you can see that at x equal to 2.5, x equal to 2.5, there is a horizontal tangent, and for the point slightly less than that, that is for x values less than 2.5, we can see that the tangent, here it is blue colored tangent, that is having a negative slope, that is having a negative slope. And for the points right to x 2.5, that is values slightly greater than 2.5, if we consider the tangent here on the graph, you can see green colored tangent, it is having a positive slope. So what is the conclusion here? We can see that at x is equal to 2.5, we are having a horizontal tangent, means derivative is 0. And for the points slightly less than 2.5, if we consider the tangent, look at the graph, the blue colored tangent, that is having a negative slope, means when x is slightly less than 2.5, you can see that the derivative is negative, means slope is negative. And for point x greater than 2.5, you can see the tangent at such points here on the graph, green colored tangent, they are having positive slope, means derivative will be positive. Consider the function f of x is equal to x square minus 5x plus 6. I told you at the point of local minimum or maximum, the tangent is horizontal, means its slope is 0, means derivative 0. Therefore, at the point, for the point of local maximum, for the point of local maximum or local minimum, you can see that f dash x should be 0, which implies f dash x, what is f dash x here? 2x minus 5 must be 0. So which gives you the critical point x equal to 5 by 2. Critical point means we have to check whether this point is a local maxima or local minima. That test we have to perform. For that, we consider the x value slightly less than 5 by 2, which implies 2x minus 5 less than 0. What is 2x minus 5? 2x minus 5 means that is derivative. So derivative less than 0. That is left hand side derivative is less than 0. And when x is greater than 5 by 2, then what happens? That is 2x greater than 5, which implies 2x minus 5 is greater than 0, which implies derivative, because 2x minus 5 is derivative, f dash is greater than 0. That is happening on the right hand side. So we can conclude that when x equal to 5 by 2, then tangent is horizontal. When x is less than 5 by 2, that is left hand side, tangent is negative, tangent is having negative slope. And for right hand side, derivative is positive, means tangent is having positive slope. So clearly from the graph as it indicates, x is equal to 2.5, that is 5 by 2 is a point of local minimum, is a point of local minimum. And we can find the local minimum value. For that, you substitute that point at which the local minimum occurs. Here what is it? 5 by 2. we have to substitute in the function. What's the function? Fx is equal to x squared minus 5x plus 6. So what is f5 by 2? That is 5 by 2 the whole square minus 5 into 5 by 2 plus 6. That is equal to 5 by 2 the whole square means 25 by 4 minus 25 by 2 plus 6. That we have to simplify. That is 25 by 4 minus 50 by 4 plus 24 by 4. That is equal to 49 by 4 minus 50 by 4. That is equal to negative 1 by 4. But here the things can be made much simpler when we apply the second derivative test. For that, what we have to do? For example, consider the same function f given by x squared minus 5x plus 6. For finding the critical point, we have to solve the equation f dash x equals 0, that is 2x minus 5 is equal to 0. So, which implies x equal to 5 by 2. So, when x equal to 5 by 2, either the point will be local minima or it will be local maximum. Then how to decide whether it is a local maximum or minimum? For that, second derivative test, by the name we have to go for second derivative. We have to find the second derivative, that is f double dash. That is what is here, that is 2. And if the second derivative at the critical point x equal to 5 by 2 is less than 0, then the point x equal to 5 by 2 will be local maxima. And on the other hand, if f double dash is at x equal to 5 by 2, after computing the second derivative value at x equal to 5 by 2, if it happens to be positive, then you can conclude that the point x equal to 5 by 2 is a local minimum, that is point of local minimum. And by chance if second derivative equals 0, then we cannot solve that problem by second derivative test. We have to go back to the first derivative test. Here the value of the second derivative, that is f double dash x at x equal to 5 by 2. Since there is no x here, we need not substitute. Automatically the simplification is over and we are having the value of the second derivative at x equal to 5 by 2 is 2 and it is positive. It is positive means I told you the point x equal to 5 by 2 will be a local minimum. So it is very easy to use second derivative test to find a point of local minimum or maximum. Find two numbers whose sum is 24 and whose product is as large as possible. So let x and y be the numbers. Then it is given that sum is 24. So you can write like this. Simply speaking, the numbers can be taken as 24 minus x and x. So what is the product of the numbers? That is x into 24 minus x. Here perchance you may wonder why we didn't take product is equal to x into y. When the function is having multivariable, that is more than one variable, such a cases of maximization, minimization, we are not dealing in plus 2 codes. So here p is equal to x into 24 minus x. We can simplify this expression as 24x minus x square. So this is our function p which is to be maximized. So for that, first of all, we have to find the first derivative, that is dp by dx, that is 24 minus 2x. And for finding the critical point, we have to equate dp by dx equals 0, so which gives you x equal to 12 here, because you know 24 minus 2x is equal to 0 means 2x is equal to 24, so x is equal to 24 by 2, that is equal to 12. And we have to check whether it is a point of local maxima or minima. For that we have to go for second derivative, that is d squared p by dx squared. Here it is negative 2, and we have to substitute the obtained x equal to 12, that is critical value, in the second derivative. That is, we have to substitute x equal to 12 here. But as there is no x in the second derivative, our substitution is automatically over. So we have negative 2 as the simplified answer, and which is less than 0, which shows that x equal to 12 is a point of a local maximum, is a point of local maximum. What is the meaning? That is, the product will be maximum. Product will be maximum when x equal to 12. And when x is equal to 12, you can find the other number, that is 24 minus x, that is equal to 24 minus 12, that is equal to 12. Hence the required numbers are 12 and 12. So that their sum is 24 and the product is 144, which is the largest possible product.
A rectangular sheet of tin with a dimension 45 cm into 24 cm is to be made into a box without a top by cutting off square from each corner and folding up the flaps. What should be the side of the square to be cut off so that the volume of the box should be maximum? We can see the sheet here with a dimension 45 cm and 24 cm, and we are cutting small squares from all the corners of that sheet and folding the flaps to get the box without a top, means open box like this. You see, we are changing the side of the square to be cut off like this. Then the various boxes are formed with a different volume. Now let us see the volume curve also here. When we are changing the side of the square to be cut off, then you can see volume is also changing. Now you can see volume is coming down, and at that point, that is volume is a maximum. Let us come back for that point, that is here, that is volume is a maximum, you can say. Now what about the height of the box? That is 5. And what about the height here? Height is nothing but the side of the square that we have to cut off from the given sheet.
A rectangular sheet of tin 45 cm by 24 cm, that's the dimension of the tin sheet, is to be made into a box without a top, that is an open box, by cutting off square from each corner and folding up the flaps. What should be the side of the square to be cut off so that the volume of the box is a maximum? How to solve this problem? So here is the rectangular sheet having dimensions, that is 45 cm length and 24 cm width or breadth. So let x be the side of the square to be cut off from all the corners. Then what should be the length of the box? So length of the box will be 45 minus 2x. And what should be the breadth of the box? That will be 24 minus 2x, and of course the height will be x units. So what should be its volume? Volume will be 45 minus 2x, that is length into breadth, that is 24 minus 2x into x. That you can simplify as 4x cube minus 138x square plus 1080x. So that is having only single variable, and we have to maximize the volume V. Now we have V is equal to a single variable function 4x cube minus 138x squared plus 1080x. We have to find the first derivative with respect to x, so that is equal to 12x square minus 276x plus 1080. And we have to find second derivative also, that is d squared v by dx squared, that is equal to 24x minus 276. And for finding the critical point, that is the point of maximum or minimum, we have to equate first derivative equals 0. That is, we have to solve dv by dx is equal to 0, which gives you 12x square minus 276x plus 1080 is equal to 0. Then which gives you have to simplify this by factorization method. You can take a common factor 12 outside, so that is 12 into x square minus 23x plus 90 is equal to 0. That is x square minus 23x plus 90 is equal to 0, which can be factored as x minus 5 into x minus 18 is equal to 0. Thus we have two values for x equal to 5 and x equal to 18. But here you can see that when x is equal to 18, we cannot make a box there, because the length is okay, that is 45 minus 2 into x 36 you can subtract. But for breadth 24 minus 2 into x, that is the breadth of our box. And here if we take x equal to 18, that is 2 into 18 means 36, so breadth will be negative. Therefore x equal to 18 is not acceptable. So the permitted value is x equal to 5 only. Now we have the second derivative. What is second derivative? This is the second derivative, and that is 24x minus 276. 24x minus 276, that is the second derivative, and we have to substitute x is equal to 5 in this one. That is, we have to substitute x equal to 5 here. When we substitute x equal to 5 in the second derivative, we are having negative 156, which is less than 0. Therefore, you can conclude that x equal to 5 is a point of local maximum. That is, the value of the volume, that is volume will be maximum. Volume will be maximum when x equal to 5. So, the side of the square to be cut off is 5 cm.
A jet of enemy is flying along the car y is equal to x squared plus 2. A soldier is placed at the point 3-2. Find the shortest distance between the jet plane and the soldier. Let us have the animation here. The flight is coming closer and closer to the soldier. We are searching for the nearest point. You see 1-3 is the point when the jet plane is nearest to the soldier. Once again please, you see it is coming closer and closer, and at 1-3 on the car when the flight will be nearest to the soldier. And we can see the minimum distance also like this.
A jet of enemy is flying along the car y is equal to x squared plus 2. A soldier is placed at the point 3-2. Find the nearest point on the curve to the soldier. Okay, consider the diagram and let this point, we don't know actually which is that point, the nearest point, but let it be the nearest point. So having the coordinate to say xy. Xy is nothing but x. What is y here? That is x squared plus 2. Y is x squared plus 2. So we can take the point which is the nearest point on the curve as x squared plus 2, so that the minimum distance will be this is the minimum distance. Let this point be capital N and this be the soldier position S. So this N's distance, let it be the shortest distance. So that N is the nearest point. Then we can find N's distance by means of a distance formula. That is nothing but, x minus 3 the whole squared plus x squared plus 2 minus 2 the whole square. That is the distance. We can take this distance as say x minus 3 the whole square plus x squared plus 2 minus 2 means x power 4. S is equal to square root of x minus 3 the whole square plus x raised to 4. Here let s is equal to s squared. Why? Because when s is minimum, automatically capital S also minimum and vice versa. So here we can have very easy computation by doing the square process. So small s is equal to capital S squared. What is it now? That is x minus 3 the whole squared plus x raised to 4. Then we have the function s, that is x minus 3 the whole square plus x raised to 4. Then we have to find ds by dx, that is equal to 2 into x minus 3 plus 4 into x cube. Now we have to find the critical points by equating this ds by dx is equal to 0, which implies 2 into x minus 3 plus 4x cube is equal to 0, which gives you x is equal to 1. Now we have to check this critical point with the second derivative. So we have second derivative, that is d squared s by dx square, that is equal to 12x square plus 2. And we have to find the value of the second derivative at x equal to 1. So here when x equal to 1, this gives you 14, which is positive, which shows that when x is equal to 1, we can say that small s will be minimum. S is minimum means capital S is minimum. That I told you, s is equal to s squared only. So whenever s is minimum, then s squared will be minimum. So when s is minimum, capital S is minimum. And what is capital S? That is ns, the distance is minimum. So when x is equal to 1 means what is y value? That you can compute very easily. When x is equal to 1, what is the given? Y is equal to s squared plus 2, so which gives you 3. So you can conclude that 1, 3 is the point on the curve which is nearest to the soldier. So dear learners, calculus has been a wonderful tool to solve such a problem of optimization. Optimization problems means a problem of minimization or maximization. Okay.